Let's talk about wave functions. Now, 2 videos ago, we started talking about matter waves. And then the next video might have seemed a little out of sequence because we started talking about atomic spectra. And it seemed to have nothing to do with matter waves. It was all about these fixed energy levels. And the fact that we could explain the reason for discrete line spectra because electrons would drop energy levels, and when they did so, they would produce a photon with an energy equal to the difference in the 2 energy levels. But we never answered the question, why did Bohr think there must be stable energy levels? We never gave any of Bohr's physical reasoning. And that's what we're going to try to do in this video. So we're going to apply the idea of matter waves to the atom and thereby explain why we should get fixed stable energy levels in an atom. Now it's going to take until the end of the video before we can explain how matter waves explain atomic energy levels. And what we need to do first of all is get a better physical understanding of what a matter wave is. And the first thing you really need to know is what a matter wave is not. So if we're considering the matter wave for an electron, a matter wave is not an electron bobbing up and down. That's not true. These matter waves are purely mathematical. And what that means is they don't describe localized electrons. They only describe the probability of finding electrons in different places. So what we'd like to do now is go a little deeper to explain what a probability wave would be. And we want to do that in terms of what we already know about waves. And one of the things we said about waves was that intensity is proportional to the amplitude of the wave squared. Now intensity, of course, that's power per unit area. So if we were talking about an electromagnetic wave, that would be the rate that the photons strike a unit area. Or now, of course, we're going to be talking about matter waves, say electron waves, and so that would be the number of electrons striking per unit time over a given area. So let's say we imagine we've got a screen that's detecting electrons striking that screen. And every time an electron strikes the screen, it leaves a dot, and let's say it leaves a pattern, something like that. Then we could say that we have high intensity in these regions. Now, if we hadn't made those detections, it would be nice if we had some theory that would predict where we'd get high intensity. And of course, we're going to get a high intensity of electrons where there's a high probability of finding the electrons. In other words, intensity is a measure of probability. Intensity and probability are proportional to one another. And if intensity and probability are proportional, and intensity is proportional to amplitude squared, that means that probability is going to be proportional to amplitude squared. So we're going to be able to calculate probabilities from the amplitudes of waves. Now the probability waves that we'll be interested in will actually be standing waves. Now that might seem strange because standing waves are formed when waves pass through each other. And in the cases we'll be looking at, we'll only be looking at one electron or one wave at a time. But you'll recall when we had, say, a wave on a spring, the wave would interfere with itself because it would reflect off the endpoints. And so we'd get the interference because of those boundary conditions. Or we could say we get interference because the wave was confined. And so when we're talking about, say, an electron in an atom, of course, our wave is confined. It's confined to the atom. So it's the standing waves that are going to be important for us. And you'll recall the graph of a standing wave. It would be a graph of displacement versus position. And it looks just like a regular wave, except it's not moving. It is oscillating, but it's not moving. So we usually represent the oscillations with a dotted line here so that we know that as this antinode is oscillating downwards, this one's coming upwards and that one's going downwards, and then we'd have these fixed points here that we'd call nodes. Now, you'll also recall that every single point on the standing wave is like a little oscillator, oscillating back and forth here. Any point would be oscillating back and forth as a simple harmonic oscillator. And of course, each oscillator would have its own amplitude. We'd have amplitude 2, amplitude 1, etc. So the displacement here is like the amplitude with a plus or minus thrown in. Now, it's really the amplitude squared that we're interested in. So let's do a graph of the amplitude squared. Still be against position, but of course when we square the negative amplitudes, we'll get positives. So all the values are going to be positive, and we're going to get a curve that looks, it should look something like that. And the way that we would read that graph is we could pick out a region in space. So maybe we pick out this region here. And we'd notice that the amplitude squared is really, really small in that region. And that means there's a very low probability of finding the electron in there. If we looked in this little region here, we'd have a very high average amplitude squared, or high probability, and that would mean there would be a large probability of finding the electron in that region. Now, of course, there's a lot of fancy mathematics involved in the real process. You've got to use integration, and there's a process called normalization that's used so that physicists and mathematicians can calculate the probability of finding the electron in a given region. Now, when all the fancy mathematics and the normalization process is carried out, each particle, or say each electron, will be represented by a traveling wave. And we use the Greek letter psi to represent that traveling wave. And it'll be a function of both position and time. So it's a moving wave. Now, sometimes you'll see the capital Greek letter psi as well, but it means the same thing. When we take this psi and we square it, we get the probability density. And we really have to talk about it as a density, because we can't talk about the probability of finding an electron at a point in space. We can only talk about finding the probability in a region of space. And that's going to involve some integration in order to determine that probability. Keep in mind, the IB will not ask you to do any integration. So the only questions they can ask you is to see if you have a basic understanding of what is meant by a wave function. So here's a typical question. Pause the video, try the question, come back for the answer. So here's phi squared, and it's proportional to the probability. If you search for the electron in here close to A, well, that's where there's a high probability of finding it. So you're most likely to find your electron close to A. So let's come back to this question of why there are stable energy levels within atoms. Now, you might not be aware of it, but you've already studied a wave system that exhibited a pattern of stable energy levels, just like the stable energy levels in the atom. And that example was standing waves on strings. And you'll probably recall when you were practicing making standing waves using a slinky that you couldn't just use any old frequency, that only certain frequencies would produce that standing wave pattern. And if you were off that frequency, your spring just kind of went crazy. It went into kind of a chaotic pattern, an unstable pattern. So the only stable patterns were when you fit the boundary conditions. So if we take a string that's tied at both ends, the boundary conditions were nodes at both ends. And we had a first harmonic, or we're now going to call it the lowest ground state energy level. We'll call it E1. And we'll say the length of the string is L here. And of course there was an E2, a second energy level, which was at twice the frequency. And it contained 2 nodes instead of 1. And we could keep going on. There'd be a third energy level, where there was 3 antinodes, etc. So the simple standing wave on a string exhibited these quantized stable energy level. And while we're here, I just kind of wanted to remind you the relationship between L and lambda, because we're going to need that in a minute. So remember, the distance between 2 nodes is half a wavelength. So a full wavelength in that first energy level would be 2 times L. Let's do the same thing in the second energy level. Well, that's one full wavelength. Half a wavelength plus another half a wavelength. So lambda 2 would be L itself. And then here, lambda 3, a wavelength is just to here, so that's 2/3 of L. Now I'm going to do a little trick here. I'm going to divide the first one by 1. Second one, I'm going to multiply the top and the bottom by 2. Effectively, I'm multiplying by 1, so I'm not changing anything. But now it's easy to see a pattern, because all of these have 2L on the top. So we could write a general formula for the wavelength of the nth harmonic, or the nth energy level, would be equal to 2L divided by, well, 1, 2, 3. That's the same as the n number. So we can say that the wavelength of the nth harmonic has to be equal to 2L over n. So remember that, because we're going to need it in a few minutes. So now that we've reviewed standing waves and strings, we're ready to tackle the simplest system involving matter waves, or wave functions. And that system is called the electron in a box. And we're going to find that it exactly parallels. The mathematics is exactly the same as it is for the standing wave on a string. In an electron in a box, it's simply a one-dimensional system. So you've got ends to a box, and you've got an electron inside that box. And that electron, it can move to the left or to the right. And of course, it can't get outside the box. So if we make a measurement, we're going to find that it's moving to the left or to the right, and we'll find that electron somewhere inside the box. Now, of course, our box has a length. Let's call it L again. And we know the probability of finding an electron outside the box is 0. And what that means for our wave function is that we've got to get a node at the ends of the box. So we have to have a node here, because the probability has to be 0 if we go outside the box at all. Well, that's exactly the same boundary conditions as we had for the standing wave on a string. So our lowest energy level is going to correspond to this situation where we have one antinode. That would be our ground state, or our first energy level. And naturally, when we get to the second energy level, we would get 2 antinodes. That would be our second energy level. And we could continue on, and at that nth energy level, of course, we'd get n of these antinodes. Now, these energy levels, we want to think about what kind of energy does our electron have? Well, it's moving, so it's definitely got kinetic energy. But there aren't actually any fields inside the box. And if you don't have any fields, you can't have potential energy. So the only type of energy that our electron's going to have is kinetic energy. And you'll recall that kinetic energy is a half mv squared. But another way of writing that is p squared over 2m. So our first energy level would have a corresponding momentum, p1. We'd square that and divide it by twice the mass of an electron. And our second energy level would have a second momentum higher than the first momentum. You'd square that, divide by 2m. And in general, at the nth energy level, we'd get pn squared divided by 2m. Now, what we're going to do is try to work out these energy levels in terms of n and the length of the box. And we're going to do that by using that relationship I wanted you to remember for this case here, where we have nodes at both ends, and that was that the wavelength of the nth energy level would be equal to 2L divided by n. And the other equation that we're going to use is simply from the de Broglie wavelength equation. Since the de Broglie wavelength is equal to h over the momentum, that means the momentum must be equal to h divided by the wavelength. And so we could talk about the momentum at the nth energy level and the wavelength at the nth energy level. So what we want to do is take these two equations, plug them in here, and find out the energy of the nth energy level in terms of the energy level number, and the length of the box. Okay, so remember, we're taking these two equations, plugging them into our formula for the nth energy level, and we're trying to get that nth energy level in terms of n and L. So let's do that. En is going to equal Pn squared. Well, Pn is given by this quantity here. So let's square that and put it in here. That'll be h squared divided by lambda n squared times 2m. And now let's take it one more step. We've got to replace lambda n by 2l over n. So we're going to get h squared. Lambda n squared is going to be 2 squared, or 4 times l squared. We've still got that 2m, and we've got to divide by n squared. Let's bring it up here. So when we invert and multiply, that n squared is going to come up to the top. So we'll get n squared times h squared. And then on the bottom, we'll have 2 times 4. That makes 8 times the mass of the electron times L squared. And this becomes our energy level formula for the simplest quantum system. And that's the electron in a box. And something key that you want to notice about it is that En varies as n squared. Here's a typical IB question on the electron in a box model. What I'd like you to do is pause the video, read the question, try it out for yourself, come back for the answer. Hopefully you realize that the energy levels vary as n squared. And of course the numbers n squared go up 1, 4, 9, 16, etc. So if I come down here to C and I maybe make this a 10, this would be at about 9. This seems to be at about 4, and this seems to be at about 1. So we have the correct spacing here, and C is the correct answer. So notice here that the energy gaps are increasing. And that's the opposite as the Bohr model of hydrogen, where remember the energy levels went as 1 over n squared. And so here you can see the energy gaps are decreasing, so that the difference between the first and second energy level is larger than between the second and third energy level. Another electron in a box question. Pause the video, try the question yourself, come back for the answer. So hopefully you started by recalling the energy level formula. En equals n squared h squared all over 8ml squared. And you realize that that energy is kinetic energy. So we can write kinetic energy in terms of momentum. It's going to equal Pn squared divided by 2m. So now you can take the case where n equals 1 and equate these two equations. We're going to get h squared divided by 8ml squared equals P1 squared divided by 2m. And then we can divide both sides of the equation by 2m, and then we need to take the square root. And when we take the square root, we're going to get that P1 is going to equal h divided by 2l. So the correct answer is B right here. So let's come back to our original question. Why do we get quantized energy levels in atoms? So let's start with the simplest atom. A hydrogen atom, simply an electron and a proton. And in the classical model, we just imagine a proton and an electron circling around it. But now with wave functions, we want to represent our electron as a wave. So let's do that. We've got a wave moving around the circumference of the orbit. And what you can see there is you're just kind of getting a chaotic pattern. And it's rather like when you try to form a standing wave on a slinky. If you vibrate your hand at the wrong frequency, the slinky just kind of goes chaotic. And you've got to get into that right frequency in order to get those standing waves. And it's a similar situation for this electron wave about the orbit. So if we're going to get a stable pattern, something like this is going to have to happen where the waves join up. The waves are kind of like a dog chasing its tail. And they're passing through each other and they're forming a standing wave. So we've got this standing wave. And if we're going to get a stable pattern, if we're going to meet the boundary conditions, then as one antinode heads towards the center of the atom, the other antinode would be heading away from the center of the atom. And that's only going to be true if you've got an integer number of wavelengths around the circumference. There's 1 wavelength, 2, 3, 4, 5, and 6 wavelengths around the circumference. That'll form a stable pattern. So we only get stable energies when there are an integer number of wavelengths around the classical orbit. Now we might choose to say that a little more mathematically. This here would be my 6th energy level, so I might denote the radius here by r6, or in general by rn. The circumference would therefore be 2 pi rn. And that has to equal an integer number of wavelengths. That is, you multiply an integer by the wavelength. So this here, that's our condition for getting a stable energy level. And I like this diagram by Paul Hewitt. He's just drawn out full wavelengths on strips of paper. In our first orbit, our first energy level would be formed when we fit 1 full wavelength around the orbit. And our second energy level, that would be 2 full wavelengths around the second energy level. And then 3 full wavelengths around the third energy level, etc. Now Bohr didn't write in terms of there being an integer number of wavelengths wrapped around the circumference of the orbit. He talked in terms of quantization of angular momentum. But I can show you very quickly that they're the same thing. You'll recall, this is the de Broglie wavelength, and the de Broglie wavelength is equal to h divided by the momentum, or the momentum of the nth energy level. And of course, momentum is equal to mass times speed. So this would be h all over top of the mass of the electron times the speed in the nth energy level. Now, I'm going to multiply both sides by mvn and divide both sides by 2 pi. And what I'm going to get is mvn rn is equal to n, our quantization number, times h over 2 pi. This quantity here, that's angular momentum. The mass times the speed times the radius of a particle in circular motion is equal to its angular momentum. And it's quantized in units of h over 2 pi. As a final challenge exercise for you, what I would like you to do is to prove this equation for the energy levels of the hydrogen atom. Keep in mind, these are the things you know. You know angular momentum is quantized, so mvr is equal to nh all over 2 pi. That's the first relationship. Second relationship, you know that the only force acting is the electrostatic attraction between the proton and the electron. That is, the force is Ke squared over r squared. And that's resulting in circular motion. So that has to be equal to mv squared over r. And the third thing that you know is that the energy has both a kinetic energy part and a potential energy part. So the kinetic energy part is, of course, a half mv squared. The potential energy part, it's a trapped energy, so it's going to be negative, and it will equal Ke squared all over r. And this simply comes from our equation for the electrostatic potential between charges. So pause the video, grapple with this a bit, and then come back for the answer. Okay, pause the video and see if you can make sense of my solution. Let's summarize the big ideas from the video. So the video was all about wave functions, and these wave functions stem from the idea of matter waves, but we're mathematical in nature. And the amplitude of these wave functions squared would vary as the probability of finding the electron. So if we do a measurement, our wave function is going to predict the probability of finding, say, the electron in a given region. So we saw an example where we saw a graph of the wave function squared against position, and it looked something like this. And what we could say is the highest probability of finding the electron would be close to that peak in the wave function. We then did a bit of a review on standing waves, and we looked at them a little bit differently. So we were looking at, say, a wave on a string, and we realized that those harmonics were really like stable energy levels. So then what we did was we looked at the simplest quantum system, the electron in a box. And we realized that the mathematics was exactly the same as for a standing wave on a string. And we worked out what the energy levels had to be. It was n squared h squared divided by 8ml squared. And then we got back to the real question of the video, which is why did we get stable energy levels in a hydrogen atom? So we wanted to look at a hydrogen atom. We considered the boundary conditions and the standing wave, and we realized that in order to satisfy that boundary condition, we had to have an integer number of wavelengths around the classical circumference of the orbit. And in fact, if you work that out in detail, you can find that equation that the energy levels of a hydrogen atom will equal negative 13.6 electron volts divided by n squared. But realize here that for the hydrogen atom, the energy levels go as 1 over n squared, whereas for the electron in a box, the energy levels go as n squared. And then the final thing that we did in the video was we showed that Bohr's idea of quantized angular momentum was equivalent to this condition here, which was done using wave functions. So the angular momentum, mvr, will be quantized in units of h over 2 pi. So these are really the same. And that's all for today, folks. Thank you very much.